All right, now I'd like to talk about a little bit of vocabulary to get started on kinematics. Well, let's start with kinematics. Right, this is our equations of motion. In order to understand these, we need to know the terms that go into it. So let's start with position. All right, this is a location relative to a given point. Right, if I say I'm 10 feet, that doesn't tell you anything. I have to be 10 feet from something. Even more specifically, I have to be 10 feet in a certain direction from something. So in general, we call the origin of our coordinate system our starting point. And then our position can be defined by a vector r that describes the position from the origin. So now that we have position, the next thing we want to talk about is displacement and distance. So let me draw a bigger coordinate system so we can get a little more detail. Let's say we have a position R1 and a position R2. And we start at R1 and we end up at R2. And we want to talk about what is the displacement from 1 to 2, where our positions are described by R1 and R2. All right, so I said from 1 to 2, so I'm going to draw my arrow here, and I'm going to call it delta x for displacement. When we talk about a delta, that's always the final minus the initial. Our final position here is R2, and our initial position was R1. So we're going to take R2 minus R1. And that would describe our displacement. And we note that that is a vector, right? So what I want to talk about next is, let me change my pen color here. What if instead of moving in a straight line, we went this way? I'll call this a path P. So if P is a straight line, then the length of P is equal to the magnitude of the displacement, which we call delta x. In general, the length of P is the distance. So this is the difference between distance and displacement. The distance can be equal to the displacement if we move in a straight line, but in general, it's whatever the length of our path is if we take some other path. All right, so now we have a good idea of our scalar quantity distance and our vector quantity displacement, the next thing we want to talk about is rates of change. So V is the rate of change of displacement, and that's what we call velocity. And this is actually average because I have deltas there. If we want to use calculus terms here, we would say that the V, that should be a vector, is equal to dx dt. And we use time derivatives so much in physics that a time derivative of V has its own notation, V dot. All right, what about speed? Well, your average speed is distance over time. Right, so that means that if we look at the instantaneous velocity, then the magnitude of the instantaneous velocity is the same as the instantaneous speed. Right, if we think about however fast it's moving at that moment, then that's the speed. If we consider the direction it's also moving, then that's the speed and direction, which is the velocity, which is a vector, right? So our speed is a scalar quantity and our velocity is a vector quantity because it also includes direction. All right, so the next place to go from there is to talk about acceleration. Acceleration, denoted A, is the time derivative of velocity, or the rate of change of velocity. And again, we use the notation V dot or X double dot for the first time derivative of velocity or the second time derivative of position. All right, so this brings us back to kinematics, which is what we were working up to. Our kinematics equations assume a constant A, acceleration. Now that we've set up our relationships for acceleration, velocity, and position, we can derive our kinematics equations. So all I'm starting with is a constant A. This double bar on top is a way of denoting constant, whereas you could say increasing, it would have an arrow up next to it, and decreasing, an arrow down next to it. So constant A. So what if we talk about graphs? I don't see how we can avoid talking about graphs at this point. So I have some constant value A and its acceleration versus time. What if I take the integral of that? What do I get? I get the area under this curve. Let's think about the units. I didn't define our units, so let's scroll back and add that in. Well, a distance or a displacement is clearly measuring a length, right? So that's in meters. The velocity is a time derivative of that, distance over time. So that is meters per second for our units. If we take another time derivative, that's meters per second squared for our units. So we have time in seconds, we have acceleration in meters per second squared. So if we take this integral, what we end up with is a change in velocity equal to the integral of a dt. So delta v then, and I guess really I should have some boundaries here, right? Let's use c and d instead of a and b since a is acceleration. So, or let's just say initial and final. Right, so we have our delta v, which is our final velocity minus our initial velocity, is equal to the integral of a dt. So the integral of a is ax plus, oh, well, the way I've written it as a definite integral with boundaries, we don't have an integration constant, right? That comes in from here. So we end up with the v final is ax plus v initial. That's our first kinematics equation that we've derived here. We're going to get our next one in a similar way. Let's consider our graph of velocity versus time. Where we're in meters per second and seconds. Well, we're going to take this same equation and integrate it again, right? Because now we want to look at what is an area under this curve between two boundaries. So if we integrate that, we're going to get a position, right? And we know that because we've defined these values as the rates of change, right? So if I integrate the velocity, I'm going to get the change in position. So this is an integral from the initial to final value of a, oh, that looks like a subscript. Let me fix that, a times x. Oh, that's what's throwing me off. That should be a t, right? It was a dt, not dx. Bad math habit of always using x's, right? Or x actually means something here. All right, so now we're going to take this result and integrate it. And this is again with respect to time. When we integrate this with respect to time, we have our final x minus our initial x, which is just rewriting our delta. The integral of at is 1/2 at squared. Integral of vi is vit. And we've derived our position equation for kinematics. X final is equal to 1/2 at squared, acceleration times time squared, plus the initial velocity times time, plus the initial position. That gives us our two main kinematics equations. And let's look at how that comes from our graph, right? If we look at our graph, this area in blue here is V naught times T. If we look at the triangular portion of our graph, in green here, well, it didn't change color. In green here. All right, well, if we look at this, this is delta t. If we look at this, this is our change in v, which by our equation above is a times t. And we know that the area of a triangle is 1/2 at squared. So this green area then is, or sorry, 1/2 base times height. And we've got our base of t and our height of at. So 1/2 at squared for our area here. And that's our terms here. Oh, force a habit here, v naught is the same thing as v initial. And the naught here means at t equal to 0. So that terminology is commonly used. And no subscript for v is commonly used for v final. So this, just a little note on notation here. And that's using functional notation. If I say v of t equal to v naught plus at. And this is function notation. Not v times t. Right? It's the function defining v evaluated at time t. All right, so now we have our two basic kinematics equations. X is x naught plus v naught t plus 1/2 at squared. And v is v naught plus at. We can do some algebra on these to eliminate a or t. And that will give us our last two kinematics equations. I'm going to leave that for you to do if you want to. We end up with v squared is v naught squared plus 2a delta x. And we end up with delta x is 1/2 v plus v naught times t. This one I kind of consider the average speed equation is how I generally refer to this, because you can tell that that's what you're doing, right? 1/2 v plus v naught is the average speed, and then times time gives you the displacement. So if we were to look at our graph again, let's do this in red. The average speed, my pen's slow here. There, it's finally red. The average speed would be halfway between here and here. And that area is the same as this area. So the area under that average over that time t would give you the same as the area under our curve. So that's a visual way to look at that equation. The other equation, you can talk about it in terms of energy eventually. It looks a lot like energy when we, fiddle around with some of the variables, and we'll do that when we get to the chapter on energy. But I generally just refer to it as the v squared equation. This one I call the position equation. And this one is just the definition of acceleration, right? If we take acceleration equal to delta v over t and solve for v, it gives us that. So this is our introduction to kinematics equations and the necessary language to get us through it. And I'm going to stop there before this video gets too long.